We've seen that training a machine learning model involves using an optimizer. Why is the training process for a neural network referred to as back propagation? Now that we have an overview of how neural networks work, let's see how they are trained. Here is a typical example of a neural network. All the neurons within this network are arranged in the form of layers, and the neurons from one layer feed its output to the neurons of the second layer, the layers which follow it. Now, we've seen how we train a single neuron for linear regression. We have a set of points which we feed into the single neuron, and we get a regression line. We also know that the activation function for a single neuron for the purposes of linear regression is the identity function, activation set to none. Let's think of training as an optimization problem and see what we are trying to achieve. An optimization problem has to have an objective function. It has a number of constraints to which you have to adhere, and there are a number of decision variables that you have to determine. In the case of regression, we saw that the objective function was the mean square error. We want to minimize the variance of the residuals. We know the constraints are that we have to express the relationship as a linear relationship of the form y is equal to wx plus b. And the decision variables which are tweaked are the values of w and b. This optimization problem, in the case of linear regression, results in us finding the best fit line through a series of points. This best fit line is our regression line. Now, the actual training of a neural network, just like in the case of a single neuron and linear regression, happens via a process called gradient descent optimization. Let's understand what gradient descent optimization is for a single neuron, and you can extend this to all neurons of the neural network. Imagine that we have a three-dimensional axis where the all possible values of w and b are plotted on the lower two axes, and the loss function or the cost function, which in the case of linear regression is the mean square error, is plotted on the third z axis. If you were to go ahead and painstakingly plot all possible values of W with all possible combinations of values for B and plot the mean square error, you would get a curve. And you can imagine that the curve looks somewhat like what you see on screen. This is just hypothetical though. Depending on your data set, the curve could have any shape. Now, what we are really looking for within this curve is to find that value of W and B, which results in the smallest possible value of the mean square error. That is the objective of this training function. We want the mean square error to be as small as possible, and we want to find those values of W and B for which this is true. In order to find the smallest possible value of the mean square error, we start off at some point on this curve. That is our initial value of the mean square error. That is, we've initialized W and B to some arbitrary initialization values. And from this point, we basically descend down the slope of this mean square error to find the smallest possible value. The purpose of our optimization algorithm is to descend down this slope to converge on the best value for the MSE and find the corresponding values for W and B. This is the basic function of the gradient descent optimizer and other optimizers that are available as built in library functions in TensorFlow. A neural network is, of course, far more complicated. We're not dealing with a single neuron, we're dealing with thousands of neurons spread across multiple layers. But the basic process of training a neural network is the same. We still use gradient descent optimization, but this time we apply it using a technique called back propagation. An example, let's consider that you're using this neural network for image classification. You'll feed in the corpus of images right through to the last layer till you get a predicted label. You'll compare this predicted label with the actual label and basically feed back and train your weights and biases. This feedback process is applied in a very specific way within a neural network. You'll get the output of our final layer, that is the object parts layer as is depicted here on screen, and that output you'll use to train the weights and biases of the input into that layer. This is back propagation because once you've fed forward the images and got a predicted label, you'll use this predicted label to tweak the weights and biases of the last layer. After adjusting the weights and biases that feed into the last layer, you'll go to the previous layer in the sequence and train the weights and biases of those layers. You'll move backwards and train the weights and biases till you get all the way to the input layer. The weights and biases are propagated backwards through the neural network, and at each step, you apply the gradient descent optimization or some variant of that optimizer in order to tweak your weights and biases. It's the same optimization algorithm, but this time applied to layers of neurons in a neural network and propagated backwards from the outer layers. That's why it's called backpropagation. This backpropagation it is what allows the weights and biases of all connections within your neural network to converge to their final values. While training a neural network, we feed the training data in a feed forward manner through the layers of the neural network. Once we get the output, the predicted output, we use the predicted output to measure the loss or the cost using our objective function. Now, this objective function is then used to tweak the weights and biases of the last layer or the output layer of the neural network. Once these are tweaked, these are then used to tweak the weights and biases of the previous layer. Thus, we move backwards, training the weights and biases of a neural network. We work backwards from the output layer back to the input layer, which is why it's called back propagation.